For work in circular motion, work is equal to torque times the change in angular displacement. But why does this make sense? Well, if we look at the situation above, ds is our small change in distance in the circular motion. The length of the radius of the circle is going to be r. We also know in general work is equal to force times displacement, where F is the force and d is the displacement. So if we apply this to our situation, we can see that the force is going to be F perpendicular, which is perpendicular to the axis of rotation. D is our displacement, which is going to be equal to ds in this situation. We get this expression here, but since it is ds, which is a small change in displacement, we know we're going to be looking at a small change in work. So we can write work as dw. We also know that for a small change in angular displacement, ds, we have this relationship here, which ds is equal to rd theta. So we could plug in rd theta for ds in our expression. Then we can look at this part here, noting that torque is equal to force times length, which is also equal to FL sine phi by the cross rule. Since we're looking at force perpendicular, and we know that phi is the angle between force and the length, in this situation, the length is equal to r. And so if we draw our circle here, the angle between r and the force perpendicular is 90 degrees. Sine 90 is equal to 1, and so the torque is equal to F perpendicular r. So we can note that this term here is going to be just equal to the torque, so we can plug that in, which if we do that, we get this expression. Then we can just simply take the integral of both sides, knowing that the work at the beginning is going to be equal to 0. If we take the integral of both sides, we get this expression for the final answer. This is why the work for angular displacement is this exact equation.